This video is sponsored by PCBWay. Welcome everyone. In this video I show you step by step how I designed the PCB for my most recent CH32V006K8U6 development board. I show you how I assembled the schematics and picked the components, and then I show you how I laid out all the components on the PCB. I do all the PCB design process in Kicad 9. Then I show you how we create the production files, also known as Gerber files, and place an order at PCBWay's website. So we jump right in the middle of the things, and I already have Kicad open, and I have already created a new project with this name here, and this will contain all the design files that we need for this demonstration. So first we open the schematics. So we have the schematics here, and the first thing that I would like to do is to place the microcontroller on this sheet. But unfortunately, the microcontroller does not exist in the standard libraries, so we actually have to create a symbol for it. So we jump back to this main page and we open the symbol editor. And then what we have to do here is that we have to create a new symbol. So for that, we open File and we have to create a new library because we cannot save our new symbol in an already existing standard library because they are not allowed to be overwritten. So we create a new library. I make it global, so it can be used by other projects in the future as well. So here you can see that under the documents, Kicad 9 and symbols, I already have a bunch of libraries. They are for other third-party components, and I actually already have some test libraries here, but I want to add a new one just so I can show you how this whole thing works. So we name it, and I will name it according to the name of the microcontroller. So I call it like this, and then I just save it. And now we have the microcontroller library here, so we can create the symbol. So when we click the new symbol, we have this pop-up window, and the symbol name will be obviously the chip's name. And the designator is U, because that is used for chips, and then everything else is left on the default setting here. So we get this letter here, I zoom out, and then we have to draw a box, and that will be the box or the outline of the symbol. So I just drew a ridiculously large symbol here, and then I change it by double-clicking it. And then I apply a fill color here, so we can see that we can fill it up with the background color, and we can also fill it up with a certain color. And I just picked the default color, as you can see, so it will look like as a standard chip in the library of the Kicad software. So far so good. We have the designator here, and we have the, let's say, body of the chip. And it needs pins, but we have no idea about where to put the pins and how to name them and so on. So we open up the datasheet of this microcontroller. So this is the datasheet, and we are just searching for the pin diagram, and we are looking for the K8U6 microcontroller because that's what we want to implement, and this is how it looks like. So what we need to do is that we basically have to copy paste this into our Kicad symbol. So here we can select draw pins, and then we can name the pin, and this will be VSS. This will be pin number 0, and this is a power input, and then it will point upwards. So then we can put it here at the center of the chip, but pointing downwards. Why I do it like this is because typically when we draw schematics, then we want the ground pointing downwards because it has some kind of visual guidance as well. So this is how I will do it. And basically that's what we need to do here. And then I go back to this, and we have the VDD pin, which is pin number 17. And then that is also a power input, but this has to point downwards in this designer, and it will look something like this. So now we have our chip. I don't care about the proportions and everything because I know that I need a bunch of other pins. I will arrange that later, but we have the power pins laid out. Then we can move on and place the GPIO pins, and we know that we have already used up 2 pins, so we have still a bunch of left because this is a QFN chip, so it has many pins. In this specific case, it has 32 pins plus 1 because the numbering starts from 0 and then it goes up to 32. So now I start from the first physical pin, so pin number 1, which is PB3. And what I usually do is that I also write the secondary function here after a slash, and this is SWCK. And this is what I care about, these 2 functions, and this is pin number 1. But now this is a bidirectional pin, and then I will make it point right. And then I just put it here, and it's done. And now what we can do is that we follow the datasheet, and let's say we put 16 pins on the left side and 15 on the right side, and we just do this repetitive task. And how we can speed up this is that we can select this, then we can press Ctrl and the letter D, so we duplicate it, and then we neatly put it under it, and then I just double click this. So then the next pin will be PA5, and here I don't have any, let's say, secondary stuff that I can write here or I want to write here, so I just leave it as PA5, and this is pin number 2. And it's done. And then I just have to do this repetitive task. So once this task is done, then we will have the full chip. So the chip is done, and you can see that we have all the pins here now, and some of these pins, as you can see, have secondary or even ternary functions written. So that will help us to connect everything to it, because we will see what each pin does. And of course I also left some pins empty, but you can always refer to the datasheet if you want to use their extra or alternative functions. So now we can select this chip and we can assign a footprint to it, because this is just the symbol in the schematics, but when we put it on the PCB, it will need a footprint. So we go and open the properties of this chip, and then we can see that everything is empty here. So I just copy paste this as the value, and you will see that that will show up somewhere here. So I just press OK just to show it. So now we also have the chip's name here, and when we import this part into our schematic, it will show up there nicely, so we know what is the chip's name. And then we go back and we assign a footprint. So for the footprint, we can look at the datasheet again, and this is just a typical QFN32 package. So we can see that it's a 4x4 millimeters chip, and then it has the pins aligned like this. So we can see where it has the pin number 1, and then we can go that in this specific drawing, the pin numbering goes from pin number 1 clockwise towards then pin number 9, 16, and so on and so on. And we can see the pitch of the pins, so 0.4 millimeters, and each of these pins are 0.2 millimeters wide, that we can see it up here. And then we also have this sheet or this plane at the bottom, which is 2.7 millimeters wide, and since it's a square, it's also the same height. So we have to find a package which is close enough to this, but since this is a standard part, we can find it in the library, hopefully. So we have the library here, and we just simply start to search for QFN32, and then we get a bunch of standard parts here, and we know that our chip is 4x4 millimeters, and the pitch of the pins is 0.4 millimeters, and then the plane at the bottom is 2.7 plus minus 0.2 according to the datasheet. So this 2.65 times 2.65 millimeter, which is this red area here, will be more than perfect. So we select this and press OK. And then now we see that the footprint is assigned to this part as is. So we press OK here again, and then we just simply save it. So now we have our custom microcontroller, and we can return to the schematic editor. So we can see the empty field here. So I just go to the browser, and then I search for my CH32 microcontroller. So here under the symbol, which I named like this so I can easily find it, I have my own symbol, the corresponding footprint, so I just select it and place it in the center. Later on I will move this to somewhere else within this sheet, but now it should be in the center so we can discuss it easily. So now we are back to the data sheet again, and we can see that the recommended power supply looks like this. So there should be a bypass capacitor between VDD, so 3.3 volts, and VSS, ground, and it should be a 100 nanofarad capacitor. So let's start with that. So let's get back to the symbol browser again, and let's search for a capacitor. So I just select this very simple capacitor icon here. So we come a little bit closer and we can immediately assign a value, so 100 nanofarads, and then we can move it closer to the VDD pin, which will look something like this, and we just simply connect it together, and we can place the power pins. So that is under the power symbols icon here, and then G and D will bring us the ground, so I just place it here, and then after a little cleanup here, I can put the 3.3 volt here. So then we create a 3.3 volt label, and that will feed power to the microcontroller. And then I just click on the ground, press Ctrl D, duplicate it, and place it here. So now our chip has a power. So now this is nice, but we have to get back to the capacitor, double click. And then you can see that the footprint field is empty. So I click on this. And then I select an SMD capacitor. And I want to make this board to be able to be assembled by hand. So I select the 0603 size, which is relatively large when it comes to SMD parts. So this is large enough so we can use a small tweezer and put it on the board. So this will be fine. And then I just assign it and press OK. So this is good so far. And then now we have to do another tedious task. At least I want to do that now. So you can see that we have all these pins, but they don't go anywhere. And in order to avoid clutter, when we, let's say, wire something, I don't want to wire like this, that I just run the wire across the wall drawing. I will put a label on each of these pins according to the names here that we can see. And then when we have another, let's say, circuit component or another area on the circuit, then we can just duplicate the labels from here, put it there, and then that will automatically connect the two parts together without drawing a wire between them. Here we have the global labels option, and then we just click it, and then we name the label, for example, PB3 or SWCK. And then we created a label. Pressing the R letter lets me to rotate it, and then I just simply place it on the pin. And now we have a label here, so I can just select it and press Ctrl D, so that will duplicate it. I place it on the next pin, and then double clicking it will open the properties form, and then I can just name it as PA5. And then I continue this until I fill up all the pins here. So this is done. The pin has all the labels. So when we want to connect this label to somewhere else, we just click on it, duplicate it, and bring somewhere else where it is needed. So I zoom out, and then I place this at the corner here. And then, just to make it more aesthetic, I create a box around it. So I know that this is done. And even we can write the microcontroller's name here, so we know what is inside this box. Now we can focus on the peripherals, and I think we can start with the USB connector first. So I zoom out a little bit, and then I go back to the symbol browser, and then I search for USB-C. So we have these options here, and I always use this 16-pin connector. So I just add this to the circuit and place it, let's say, up here. So first we check the connector. So I double click it, and we can see that we don't have a footprint assigned to it, so we have to assign one. And this specific one is the 4105, and this is it exactly what it shows up from the standard library. So I just press OK on this, and then we have a correctly assigned footprint. So this is done. So now we can focus more on the connections. So I take the ground from here, Control D, and then I come closer so we can see things better, and I just put it on the ground, and then I duplicate it again and just put it roughly here. So we have the shield here, and for RF reasons people usually pull the shield to ground through a 1 megohm resistor plus a 4.7 nanofarad capacitor in parallel with this resistor, but I think that that's a bit overkill, so I just add the 1 megohm resistor here to hopefully mitigate some of the EMI issues. But this board is not specifically an RF board, and it's just a development board for hobby users, so it will never have to go through like EMI inspections and stuff like that. So I think we should not focus on this too much. So all I do is that I search for a symbol, and I search for a resistor, and then I just add it to the circuit here, and then I double click the R, write 1M here, and then I double click the resistor, and then I search for a footprint, which should be a resistor, and 0603, because our capacitor that we already placed to the microcontroller has the same size. So then we press OK, and then OK here, so we have a footprint, and finally we connect everything here. So this is done. Then we have the SBU1 and SBU2. Those are not connected to anything, so I have this no connection flag and place it on both connectors here. Then we have the USB connectors. So what I usually do is that I connect them together, and then I create a label, and I call it D+, put it on the D+, and then here I create D-, obviously. Then we have CC1 and CC2. So what we have to do here is that we have to put a 5.1 kilo ohm resistor on each of these pins and connect it to the ground. So this will set the device as a power sink, and if we are using it with a USB 2.0 standard connection, then the device will be able to draw 500 milliamps of current. And if we have a USB 3 connection, then it would be able to draw up to 900 milliamps, but we don't need that much current here. So what I will do is that I take the already placed resistor, because this already has the footprint assigned and everything, Control D, and then put it here. And then I double click this value and just write 5.1K, so this has 5.1 kilo ohm resistance. And then I duplicate this, put next to it, so everything is laid out nicely. So first we connect them together, go to the ground, duplicate, Control D, put the ground there, and then connect here and here. So now our device is fixed. And then we have the V bus. So the first thing I want to do here is to put a fuse on it. So I go back to the symbol browser and enter fuse. And then I should get this polyfuse and press OK. Rotate by pressing letter R, placing it here, connecting it, and then we need a 5 volt power rail. So I just go here, +5, and place it here, and then connect it together. So my plan here is to add a 500 milliamp fuse here. It will be a resettable fuse. So that means that once the current trips the fuse, and if we stop the current, then the fuse can recover itself and it can be used again after a while. But this has to be also assigned with a footprint. So we double click this, and the footprint of this one should be 0805 because this is a fuse. So it's a bit larger than the other parts. So we have the part in the standard library. So we just press OK and OK. So everything is clear with the USB connection now. And the fun story here is that I've been using the wrong fuse in many of my projects, and not from like part perspective, but from price perspective, because in the past I just searched for polyfuse on Mouser, and then the component that I found, it was from Little Fuse, and it cost me $1.95 per piece if I bought at least 10 pieces. And when I was assembling the bill of materials for this specific circuit, I was shocked that actually this single part takes up like 50% of the bill of materials, because the rest of the components are so super cheap as compared to this. And then I did a more thorough research and search, and I figured out that there is another manufacturer which sells their stuff for $0.095 per piece if you buy at least 10 pieces. So I was buying these parts 20 times more expensive than I should have. But now I have the cheaper part on my bill of materials, and my board therefore costs very cheap. So since this part of the circuit is done, we can frame it and put it on the wall. So this is that. I just put it a bit closer here, so it looks nicer. So now we can see that actually the circuit now gets power, but this 5 volt cannot get to the 3.3 volt. So what we need next is a voltage regulator. So we create the voltage regulator for this circuit. And the part that I picked is the Texas Instruments LP5907 MFX-3.3 chip, which is a low noise, low quiescent current regulator. So this will be also good when you want to use the board for low power applications, because the voltage regulator doesn't consume that much current when it is not running, when it is in kind of standby mode. And we can use a low dropout regulator instead of a DC-DC converter, because the voltage difference between 5 and 3.3 volts is very little, and we also don't consume that much power. So therefore the power or heat dissipation through the chip will not be so high, so we don't have to worry about this part. So it is a very low power circuit, and therefore we can use this regulator. So we go to the symbol browser again, and we search basically for this LP590, and you can see that a bunch of parts show up here. We need the 3.3. It doesn't matter from like drawing perspective, they are all the same 5-pin units. So, but for the bill of materials it matters, so we select 3.3, and then we place it somewhere here. Again, time to visit the datasheet, and this is our datasheet here, and the most simplified schematics. So the reason also why I picked this device is that it needs only 2 capacitors on the input one and on the output one, and that's all. And we will use this in a constantly on mode, so the enable will be tied to the input voltage, and then the ground will be on the ground, and basically that's all. So we keep this part in mind and we continue the circuit. So we already have capacitors, so I go to this C1 and duplicate it by Ctrl D and bring it here, and then again duplicate and bring it here. So then I zoom in a bit. As I said, the input has to be connected to the enable, and then we saw it on the schematics that this has to go here and this has to go here, and then they just go on the ground. So I just tie everything together like this, and then I go back and duplicate the ground, and let's say I put it here. Not the most aesthetic drawing, but it will look something like this. And we remember that on the input side we have 5 volt. So again, I borrow this 5 volt power pin here and place it here. And on the output we have the 3.3 volt. So it has to be part of the 3.3 rail, something like this. It's not super nice drawing, but it does what it has to do. And we remember that they were 1 microfarad, so we have to modify this. I just copy, and then here I just paste. So this is there. To be sure, we click this chip twice, and then we can see that the footprint is already assigned to it. And we don't have to worry about the capacitors because we cloned them or duplicated them, so they are already having the assigned footprint, but just to be sure, I show you that this has the correct footprint assigned. So this circuit is done. Let's frame it, and then let's write what is this. So this is a 200 milliamp low dropout regulator, and then we can put it next to this part here, and this is done. And in addition to this, I would like to have a power indicator. So that is basically just an LED and a resistor. So let's do that. So I get the resistor from here by duplicating it, and then we go to the symbol browser and we search for an LED, and we just add the generic symbol to it and do it like this. And then the LED will be fed from 3.3 volts. So it will be like this, and it needs a ground to complete the circuit. And then I'm planning to use a red LED. I just write it here. So we know what are the characteristics of a red LED, and I'm not going to detail it there because you can look it up, but I roughly need 1 kilo ohm resistor to reach an appropriate brightness. So I will use that, and this is basically done. So I just put it maybe here and frame it. So this is our, let's say, power indicator. And of course we also need to assign the footprint for the LED. So that's we do like here, and then we look for LED and 0603, and we just add it and press OK. So this is good now. Then in the next step we can add the reset circuit, and first we have to see how it behaves. So we can see it here in the datasheet that it has an internal pull-up resistor. So the status of the reset pin is high by default. And then what we do here, you can see that here is a momentary switch, and when the switch is pressed, then the circuit between the reset pin and the ground is complete. So then this circuit will be pulled to ground. And then to filter out the jitter when you press or release the button, the manufacturer suggests a 100 nanofarad capacitor. So what we need to have here is that basically the reset label has to be connected to this kind of circuit, which is a switch and a capacitor in parallel. So both are going to the ground on their, let's say, other side. So we have to do this. And actually I found a very nice switch which I've been seeing on other designs. So this is the switch from C&K as the manufacturer, and why I'm showing this to you is that I want to show you how to import the specific part to your library, for example using Mauser's models, because this specific switch does not exist in the default library, like explicitly. There is another switch that you can use as an alternative, but I would rather use these symbols so I can also show you how to import stuff, because that will be also useful for you in the future if you are designing other parts and those parts are so custom or so new that they are not yet included in the standard library of Kicad. So what we can do here is that we have this section which is called ECAD model, and we can see that actually Mauser provides a PCB symbol, footprint and 3D model. So we can click on this, and then we get this nice pop-up window, and even here in the 3D viewer we can see how the button will look like. So actually what we want to do is that we want to get the symbol and the footprint in the schematics editor, and then we want to get the 3D model in the PCB editor. So actually we will need to register here, but I'm already a customer, but if you are not yet a customer you have to register, and then you can download the CAD models. So after you downloaded the model, you will see a folder like this, and if you open it, then you see a bunch of subfolders here, and they are for different design software. But for example, the 3D is the generic 3D file which we can use when we assemble the PCB and want to see the 3D image of our design. So what we can do here is that we can unpack this file into a specific folder, and then that specific folder for me is under the documents Kicad 9, and then we can see that there's a bunch of folders here. So I just basically have to drag and drop this file into the 3D models folder. I already have it there, so it will ask if I want to replace, so I don't do it. But that's what you need to do. And then we go back to the zip file and go to the Kicad folder. And then we can see that we have a bunch of files, but two files which are more interesting for us is the one which has the extension of Kicad_mod and the Kicad_sim. So first we look at the sim ending file, and that is our symbol. So then we have to go back to our Kicad library, and we have a folder which is called symbols, and then that sim file has to be copied into the symbols folder. And similarly, this Kicad_mod has to go in the footprints folder. So for example, if I open this, you can see that I have a bunch of files which end with Kicad_mod, because those are the footprint files. So then we have to come to the main window of the project manager, and then go to the Manage Symbol Libraries menu. So in this Symbol Libraries browser, we can go to the bottom of the list, and we can see that we have a bunch of stuff here. I actually already added the switch here, of course, because I have already done the design. But how to add it is that we have to create a new row in the table, and then I call it switch 2 or something like that. And here we have this browser thingy here. And I know that the symbol was called like PTS8 something something. So I just open this, and then now it is in the symbols library. And then I just press OK. So then the symbol will be available in the schematic editor. Then we have to do the same, but with the footprints. So Preferences, Manage Footprint Libraries. And this is a bit more simple, because if we go to the end, we can see that there is one single folder which stores all the third-party stuff. So if I open this folder, then it is looking for a folder, so I cannot select like individual files. So then I just have my third-party folder, and then I just select that folder, and that's that. So then I return to my schematics editor, and then I search for that switch, which was called PTS something. So this is this switch. And then I just place it here on the sheet. Again, we visit the data sheet. We can see that we have 4 pins, 1, 2, 3, and 4. 1 and 2 are on the same rail, and 3 and 4 are on the same rail, as you can see it on the circuit diagram. So when we press the button, then the 1 and 2 pins, which are already tied together, are shorted together with the 3 and 4 pins. And when we release the switch, then the connection between these two become broken. So there is no connection. So what I will do is that I will not wire everything on the schematics, but I will just use pin number 1 and pin number 3. So how that will look like is that I will first borrow a capacitor again, and I borrow the 100 nanofarad because we will need 100 nanofarad, and then I just put it in line with the COM1, and then I just connect it. I borrow a ground, and then I put it slightly under here because I need to run this pin to the ground, and I need to do this. So this is done. And since I said that I'm not going to use the 2 and 4 pins, I just mark them as no connection. And the COM1 has to be the reset pin. So we go to the reset pin here, duplicate it by pressing Ctrl D, and let's say I put it here and just connect it here. Not the nicest layout, but it looks like this. Place it here, frame it, and we have a reset circuit. So now what we have here is that based on the datasheet's recommendation, we have the capacitor, and then at one of the pins, the reset pin is connected. So that's nice. And then when the button will be pressed, then internally the COM1 is connected to NO1 here. So therefore the reset pin will be pulled to ground. So it's that simple. Then the next step is the oscillator. So again, it's time to visit the datasheet. So we can see that we have to have a 24 megahertz crystal here, and we have 2 capacitors here, which are connected to the ground. So those are the load capacitors. And then the 2 pins of the crystal oscillator go to XI and XO. So So we have to find a oscillator which runs at 24 MHz, and then we have to incorporate it in our schematic. So that will be this product from Kyocera, and we can see that this is fairly small, 2 times 1.6 millimeters, and it has 24 MHz, and its load capacitance is 6 picofarad. So let's open its datasheet, and then here is the only important part, is that the crystal pins are 1 and 3, and 4 and 2 are ground pins, and that is stated in this table here. So we have to select that in the editor. So how we do that is that we place another symbol, we search for crystal, and then we select this, which is crystal underscore GND24, where 2 and 4 stand for the pins which are connected to ground. And that's what we just looked at on the datasheet. So I just press OK and put it on the circuit. And I immediately open this and assign a footprint to it. So again, we search for a crystal. And we remember that our crystal was 2 times 1.6 millimeters. So we search for that. It has to be an SMD, and we can see that we have a footprint for that. So this is a 4-pin and 2 times 1.6 millimeter package. So we accept this and press OK here. Then we know that 2 and 4 are ground pins. So I will move this a bit here, magnify it, and then I add ground here and here, and then I connect this. This is not the nicest way to do it, but it is what it is now. And then in the next step I have to add the capacitors. So I clone a capacitor here and another here. I move these text out of the way, and then we know that these two guys have to be connected to their corresponding crystal pins. So this goes to 1, this goes here, and then they go to ground. And don't judge me for my ugly drawing here, but yeah, it does the job, so it will be fine. And then we have to add the X, Y, and XO pins. So we go back here, and that is here, PA1 and PA2. So I held down Shift and selected multiple items here, Control D, and then I go back here. So let's say XO comes here, again, just ugly, but it works. And this one also goes there. So this is good, but we are still missing something. So there is a reason why I said that the load capacitance of this thing is stated on the datasheet of the crystal, which is 6 picofarad, because to be able to run this crystal properly, then the load capacitors have to be matched with the load capacitance of the crystal plus the stray board capacitance. And there is a formula to calculate the values of these capacitors. They have to be identical, of course, but by plugging in the load capacitance of the crystal and the stray capacitance of the board into this formula, we get 4 picofarads for these. So I just change this to 4 PF and this to 4 PF. And now we have to assign footprint to them. And why we have to do that is that because it is a bit harder to find proper 4 picofarad capacitors at 0603 size. So I most of the time use 0402 for these capacitors, which are helping the crystal. So then I just go here and then I change this to 0402, and then I just press OK. And we can do a trick, is that we can Control A here, select all, Control C, and then I go to this, and then I just replace it. So I just pasted it here, this text, press OK. So now both of them have the same footprint. So this is done. Let's put it here and let's frame it. And with this, our oscillator is done. And one thing that we have to notice here is that now we sacrificed actually PA1 and PA2 from the GPIO pins of this microcontroller. So they are also A1 and A0, so we did not only sacrifice 2 GPIO pins, but we sacrificed 2 GPIO pins which are also ADC capable. So if you don't want to get rid of the ADC, maybe you have to use the internal oscillator of this chip. It has, but then every, let's say, timing critical stuff, so for example, communication, timers, PWM and stuff like that, they will not be that much accurate as they would be with using an external clock source. So I would rather add an extra unit, for example, an I2C or SPI AD converter, but I would still keep the external oscillator, and I would not rely on the internal oscillator just to gain 2 more ADC channels back. So this is that. So now we have more components, but what I want to do here is that since the microcontroller has 2 USART channels, then I want to utilize one of it and want to have a USART to USB converter. And to really simplify everything, I will just use the CH32V006K8U6 chip, which is really just an 8-pin, very simple chip. And we will rely on this to do the USART to USB conversion. And since we want to use this chip with 3.3 volts, we have to read the datasheet a little bit, because we can see that this chip has a VCC pin and a V3 pin. And these are only relevant or need more attention when we want to drive the circuit from 5 volts. But since we are using it with 3.3 volts, then what we have to do is that we connect these 2 pins together, so VCC and V3, and we use one single decoupling capacitor, which is a 0.1 microfarad capacitor or 100 nanofarad capacitor, and then that's that. And here we can also see one highlighted set of rows, which talks about the D plus and D minus data lines, and we just have to connect it to the USB bus without a series resistor. So that is also an important notification here. So we go and browse the symbols, and we search for CH340N, and we just simply drop it somewhere so we can see it, and then we build our circuit. So again, I borrow ground, put it here. I'm not going to use the RTS, so I just simply mark it with a no connection, and then I go to the USB connector and I borrow these 2 things, duplicate it, and bring it here. So as the datasheet said, they can go directly to the USB connector, so I don't put anything in between. And then we also know that V3 and VCC can be connected together. I just do a loop because later on I need another stuff here. So then we borrow the 3.3 volt rail like this, put it here, and we need a capacitor. So I just borrow this with the already correct value, mirror it so the text jumps on the other side like this, and then borrow the ground. So this is so far so good. And then for the sake of safety, I borrow this resistor here and then place it in series with RX and TX pins. So I just clean up a bit here. And then I just connect them. And here comes a very important thing. First, we borrow the RX and TX labels, duplicate, and then actually they are already aligned. But what is very important here is that one chip's TX should go to the other chip's RX, because while one chip transmits the data, the other receives, and vice versa. So this is a very common mistake that beginners do, is that since the pin names are the same, then they assume, because they don't read datasheets or documentations, that the RX has to be connected to the RX because they have the same name, but that's wrong. So the TX is always connected to the other chip's RX, and the RX is always connected to the other chip's TX. Or with other words, you have to twist the wire and connect them like that. So this is it. And with this, we finish this circuit. So let's frame it and let's name it. So it will be this simple. And then just let's place it somewhere like this. Then we need GPIOs. And we have, let's say, 2 types of GPIOs. One is the programming interface, so SV DIO or SVIO. So SWDIO or SWIO, however you want to call it, and then the regular GPIOs. So we go to the browser and we need a connector, or actually I usually use it like that, and we need a 3-pin connector. So I just put it here and we assign a footprint to it, and finally we found it. So this is done. We have to assign connections to it. So how I would like to do it is that we need a 3.3 volt, I put it here. We need a ground, duplicate and put it here. And we need the SWIO, so that will be PD1. So that goes here. So what we do is, this is connected here, this is connected here, and this one is connected here. Frame it, and we also name it, and then put it perhaps here. And now we have to lay out the GPIO. And regarding the GPIO, we know that we have already got rid of, basically, here we can see it, several pins, because we have PD6 and PD5, which I don't want to connect to anywhere else other than to the USB to USART converter. So 32-2 already. And then we have 2 other pins, so 30-2, 28, because 2 other pins go to the crystal. And then one more pin that I'm not going to break out is the reset. So that gives us 27 pins total, which we have to place somewhere. And then what we are going to do is that we want to have 3 volt available, 5 volt available, and ground available on these pins. So we get back from 27 to 30. So then with those 30 pins, we can split them into 2. So we have 2 15-pin connectors. So let's add them. And here we are already in the connectors. I just have to find one which is called 15. Put it here, duplicate it, put it down here and mirror it so it will look better aesthetically when I put the labels. And then let's open this and let's assign a footprint, which will be again a similar connector, but we need 2.54 millimeters. So we go here and we try to find this guy here, add it, Control A in this field, Control C, and then we just assign the same to this guy here. So now we are happy. And then here what we can do is that we can draw an imaginary line at the half of the chip. So a horizontal line between PC7 and PA0, so pin 5 and pin 21. And one set of pins, which is under this line, will go to one side of the PCB, and the other set of pins, which is above this line, will go on the other side of the PCB. And then how it will look like is that those which are above the line, they will go on the left side, and those which are below the line, then they will go on the right side of the PCB. So then here we can carefully add them. So we start with PC7, duplicate it, and then we go upwards, so PB4, and then PD1. And then here we skip these 2 pins because these are the RX and the TX pins. So then we go PB5. Then here we can see that the next pin would be PA7, which would be the reset. So if you want, you can add it, but I'm not going to add it because I don't want an external reset possibility here. I'm fine with the button. So then the next one will be PA0. And then I stop here, and actually I will use this as a ground pin, and later on you will see why. And then I move on to the next side. So here what I want is that imagine that here will be the USB connector. So then I want the power stuff next to the USB connector. So I'm zooming out here, and then I take this 5 volt and duplicate it, and add it here. And then I do the same with the 3.3 volt, and I have to rotate this, and I add another ground here, because why not? Of course I need to clean up this a bit. Where did we left is, this is where we split the board into half, so you can see that the top here is at PC7, so now we have to go to the other way, so PC6 will be here, and then PC5, and then we just continue. And this row is done, and you can see that after PD0, PA2 and PA1 would come, which are already used by the crystal. So if we would skip them and we would move to the next circuit, then PA0 would come, and that is already on the other side. So that's why I put the ground here. But if we want, and okay, let's do it, this is not identical to my design, then we can move PA0 here to the bottom, and we can eventually move the reset here. So therefore we can actually reset the board externally. It doesn't matter in my opinion for this specific application, but let's do it like this. And then, just to be sure, I name this pin row left, and then this will be pin row right. And then this is basically done. So now the circuit is complete, hypothetically. So we can do an electrical rule checker. So let's see. There are two errors. Let's see what is wrong. Yeah, this is just a typical issue here. We can neglect it. And this maybe can be done like this. Let's see if it's just a connection, but apparently not. But sometimes it does this kind of error. I would consider this as a warning, because sometimes this error is thrown, and then you have to do like this silly thing that you have to add a PWR flag. So I can just show you that if I would add these flags here and here, then this would disappear. So I don't quite understand why. So we can delete this because it's not a real error, I would say. And how we can make sure is that I run this, and then right-clicking it, we can exclude this violation here and here. So now it doesn't throw any errors. So the circuit is done here, and what we can do is that we save everything, and then we move on to the PCB editor. Alright, so we are at the PCB editor, so let's start importing the parts and let's start assembling the PCB. So here we have this button, and we can update the PCB from the schematic, so we do that. So then we get this window, we have all the parts here, no warnings and nothing so far, so we leave it as is and update PCB. So we see some error here, but I will explain it, and we will see what happens. So we can close this window, and we just place the parts somewhere, let's say somewhere around the center. And then first of all, I want to take care of these two guys, so I put them a bit aside. So my goal here is to make the microcontroller board narrow enough so I can plug it in a breadboard. And for example, if I make it 8 pins wide, so 8 of these slots wide, then I will have still two rows of pins available next to the microcontroller inside the breadboard. And how to align that is kind of very easy. That I just put this a little bit aside, and then I go to the parts browser here, and then I'm looking for a connector. So I select one pin header which has 8 pins and 2.54mm pitch, and then I place it on the board. And what I do with this is I use it as a spacer. So what I can do here is that I can make this a bit larger here, and then I take this connector, press R to rotate, and then I move closer to my connector here and align them so they snap together. And then I take this other guy here and move it here so they snap together like here. And now the width of the board is exactly 8 pins wide, as it should be. and then I can take away this part. And I immediately lock them, so I'm not able to move them, so I won't mess with the dimensions of the board. So this is the outline, and then I can immediately draw the outline of the board. So I go to the edge cuts layer, I draw a rectangle, and then I start at the top left corner here at the courtyard, and then I go to the bottom right corner, again at the courtyard, and it should be something like this. So now, if I press Alt 3, then that should bring up the 3D viewer, and we can see our board. So here are the parts which we haven't positioned on the board yet, and this is the board. And you can see that we are looking at the top side of the board and the pins are facing upwards, so I have to flip them. And to flip them, we have to press the F letter, but since this is locked, we just override the lock, and you can see that this letter has been mirrored, so it means that it is also flipped because now it's on the bottom side of the board. And I do the same here, I override the locks, and now it's good. So after pressing Alt 3 again, we can see that the pin headers are facing the right direction. And now I want to do something that is missed by a lot of people who are showcasing their PCBs on YouTube, for example. Even big content creators miss that. And I want to round the corners of the board. Because usually I see that whoever is publishing their PCBs, they have sharp edges and it's just simply ugly. So I show you quickly how to do that. So we are still on the edge cut layer and we want to create an arc. So I start from the corner and I want a 1 millimeter radius here, so that will be also the radius of the board's edge. And then I just go to 90 degrees here. When the two lines become green, that indicates that we reached exactly that angle. And then I can move around this, so I can overlay it with the edge of the board. So like here you can see it and here you can see it. And then I press Ctrl D, and then I just do it with the rest of the corners. And once it's done, I can delete the rectangle here, and then I can connect everything with a straight line. So I just do that. And now we have a board with rounded corners, and this was like 1 minute extra work. And now I want to know the center of my board, because everything will have to align with the center line. So I go to the user drawings layer and I draw a line, and I start it from the edge of the courtyard here, for example here, and then I go to the other side right here, and then if I move the tool towards the center, then it will actually snap to the center of this line. And we can prove that by just drawing simply a line here, which is exactly half of the total length. So this would be 21.32. So then I can go up and try to find the center here as well. So it has to be just 90 degrees. And then I release it. So now this is just a drawing which does not show up anywhere else than in the designer, but it will help me to align everything. And since we have the board, we can already flood the bottom layer with ground. So I go to the bottom copper layer and I draw a field zone. And how I do it is that I go a little bit outside the outline of the board, click, and then I get this window here. I select ground, and then you can see what kind of clearances I have here, what kind of other parameters. So I just use them as is, press OK, and then I just go and draw a bit larger rectangle around the board than the board's outline, so we can make sure that everything is included. And then I double click to close the zone, and then I press the letter B. So we are building the field zone, so we can check it. So this is the top, but if I turn around, then we can see, especially here at the edge, the difference. So this is skipped here because of the clearance, and then this lighter green is actually the copper filling of the bottom layer. And that's that. So we can go to File and Board Setup. And I want to show you that we can check a few design rules. So if you want to exactly duplicate this board or this kind of, let's say, design principles, then this is the clearances and tolerances that I'm using here. This is still producible by PCBWay, and it will not increase the price. Sometimes if you have funny tolerances or funny requirements or too tight requirements, then it can be that certain colors cannot be produced, or you will have to pay a higher price, but this board will be still within the cheap pricing. And then also in the net classes, we have to make sure that the clearance is kept at 0.15, and that is important because of the chip. And I show you why. So if I would put this back to 0.2 and then OK, then if I go to the chip and try to draw a trace, then I can bring out this trace, no problem, but I cannot bring out the second trace because you can see this red, let's say, border that is overlapping with the pad, and it doesn't let me to draw the traces. So therefore, I go back and I have to change the clearance to 0.15 so I can eventually bring out the traces. So this is very important with this QFN32 package, or any package which has this, let's say, tight spacing of pins. The pitch here is 0.4 millimeters, so we have to have small clearances here allowed, so we can bring out the traces from the individual pins, even the adjacent pins. But back to the board, we can now start placing components. So the first component I want to place is obviously the USB connector, so I just grab that, rotate it, and then we can see that here we have a line and the text PCB edge, so that has to be aligned with the PCB edge that we drew recently. And then you can see this pink vertical line with a cross here at J1, and that will be the other center. So I can just grab this, and you can see where is the mouse now, and I can place it by moving it with the arrow keys, and then we can see that that is now overlapping. If I could make it nicely, so let's say there, and here it's now also centered. So I just drop it there, and then I move this silk screen under the connector because I don't want to see it. So if we check, then we see the nice connector on the board. So this is nice. Now we can start placing the rest of the components. One of the easiest is the 1 mega ohm resistor, because that should sit right next to the shield. So I usually just put it right next to the connector like this, and then I will connect everything later. Then we have a fuse somewhere, which should be also placed close to the connector because that is directly related and connected to the USB voltage which is coming in. So I placed it here because I want to manage the ground a little bit here, so I need a little space, but here from A4 I can come out and pull a white trace to pin 1 here, and I just move this away, let's say here, and then we have 2 resistors which are the 5.1 kilo ohm resistors. So I hold down shift to select these 2 pads, and then I can press M and move them close, and we can see which pin wants to go where. So we can see that this wants to align this way, so I just throw it here for now, and this pin wants to align somewhere here, so I just throw it here. I don't align anything perfectly here yet, I just put them roughly at their, let's say, desired places, but then I will clean up the board once I start laying out the traces. The J2 connector, which is the programming connector, can be placed actually at the end of the board because that's relatively easy. So I grab the hole number 2, and then I bring it all the way down to the center and at the end of the board. So something like this. If I check, then it's sitting there. That's good enough. And then the next step could be the voltage regulator. So the voltage regulator has its chip, And I rotate it like this because after the fuse, we have the 5 volt coming out from the fuse, and that has to go to these pins. So it would not make sense to put it sideways or something like this. But both of the 5 volt pins, one is the input voltage and the other is the enable pin, has to face here because it's just more convenient to place them like this. Then we need C2 and C3 because those are 1 microfarad capacitors and they belong to the voltage regulator. So this is, as we can see on the marking here, it's 3.3 volts, so that should go to the output. So I rotate it like this, and then I roughly align it with the output. And this has the 5 volt label, so this has to go on the 5 volt side, something like this. And also regarding the power source, we have an LED somewhere, and we have a corresponding resistor. So I just throw them on the board, but I don't put them to their, let's say, final place. So we have a 1 kilo ohm resistor here, and that has to go somewhere, let's say here. Again, they will change their place. I just put them roughly on the board so I see how they are aligned. Then you can see that I left this side of the board empty on purpose because we have a chip. And that is the USB to USART converter. And I rotated it this way because you can see that the D- and D+ are facing towards the USB connector. So it only makes sense to rotate it this way. Then we know that this chip has 3 components. It has 2 resistors, these 1 kilo ohm resistors, which will be between the chip, TX and RX pins, and the microcontroller. So I just put them roughly here because you can see that the auto routing wants to route them this way. So this is TX, as you can see, and this is RX. So now it's also correctly rotated. And then I'm missing a capacitor, and that should be a 100 nanofarad capacitor, probably either this guy or this guy, because I remember that C1 belongs to the microcontroller because that was the first capacitor that we placed. Eventually we can check this. So if I jump back to the schematic editor while still having the component selected, then that gets selected also in the schematic editor, very convenient feature. And you can see that actually C4 belongs to the button. So I go back and I grab that C4 and bring it here because it will be somewhere here, so I don't mix it. And then I can press C7 and again go back to the schematic editor. And we can see that actually that belongs to the converter chip. So I go back and then I move that right here because it belongs here. So I tidy up a bit so they are roughly nicely aligned, and I can leave them like here. And then we have the microcontroller. So here we have to pay attention how it is aligned. You can see that a lot of pins on the bottom at its current orientation wants to go on the right side, and then many from this corner wants to go to the left side. So I just rotate it once, and you can see that how nicely the auto routing trace is spread out. So we keep this orientation. So pin 24 is facing upwards and pin 1 is facing down towards the bottom of the board. So I grab this and I put it on the center of the PCB, somewhere here, and probably somewhere here. Again, this is just a preliminary positioning because later on I will wiggle all the parts here and they might end up at a slightly different position. But the chip, I want it to sit at the center line of the board. Then the chip has a crystal. I grab it and bring it close to the chip. You can see how the 2 ground and the XO and XY pins are arranged. So I just put this, let's say, somewhere here. And then we miss the 2 capacitors, which are C5 and C6. So I bring them here. And we can see that this belongs to XI. So that comes here, somewhere here, and this belongs to XO. So I rotate it, something like this, and then roughly align it. So we can actually see that here we have 2 ground connections, and here we have 3 ground connections. So pin 2 and pin 4 can be connected together with a trace, but here I can create an island and place a few wires in this corner to bring the ground up from the bottom of the board to the top of the board. Then we have this lonely C1, and that has to come somewhere here, because you can see that it goes to pin 17. So I just leave it here, and later on I clear up things. And then we have switch 1. So that can be, yeah, wherever. I can rotate it like this, and it has actually an enormous courtyard, as you can see. But if I press the 3D model, then you can see that the actual switch is not that big. So I can be a bit more brave with the placement. But I will just bring this down a bit. And then when we see the 3D model, then we will be a bit more cautious about the placing. But it can be something like this. And then if I go back to the 3D model, we can see that the chip, the crystal, and the switch is missing. So let me show you how to fix that. So let's start with the chip first. I open this, and we have the 3D models, but you can see that the software cannot find it. So we go to the browse, and I have my 3D models folder, and I have downloaded this 3D model already from Mouser. So I just select it and edit, and now we have the button. And I don't need to align it or anything, I just press OK, and now we have a button on the board. So then we have the crystal. So this, again, the software cannot find it. So you can see that this is the default library of Kicad. I'm pretty sure it is also somewhere here, but I have hard time finding it. So I also downloaded the 3D model of the chip. It is in my library, so this CX 2016, and that's our model. So I add it, and now it's on the board. And now we only have this chip left. This is actually a regular SOIC chip, but still the software cannot find it. But in fact, it is inside the regular library. It is this 3.9 times 4.9 millimeter, 1.27 millimeter pitch. If I open it, the model shows up perfectly. So this is nice. And let's see the final board. Now we have all the components on it. So we just have to arrange everything, and we will have a functional board. So first of all, I can see that here this button causes a little trouble. So maybe I rotate it this way and bring it down here, and I can allow this to be a little bit further from the microcontroller. We are talking about maybe 2 millimeters, so that should be still enough. And this should be also still fine with the capacitor. So let's place it here. The microcontroller stays. Then the chip can stay here, but here I have a bit more crowded area, and probably bring it a bit closer here. And then I said that I want to route the trace here, so I brought this a bit up so I have space, and then I might be able to bring this also somewhere a bit more down, so I have 3-volt pins together, and I can create an island here. So this should be something like this. We can start routing things here. So what I usually do is I take the regular default trace, which is now 0.2 millimeter wide, and then I just roughly route the traces. So we have 2 pairs of pins here. D- has 2 pins and D+ has 2 pins. And how I usually do it is the following. So I start routing and start a trace and put a wire here. And then I go on the back side of the board, put another wire somewhere here, and then I switch back to the front side and I connect to it. So now I connected these 2 pins together, and then I use the D+ trace, and then I go around the D- trace with a loop, and then I just go back here. So this should be sufficient to connect everything. And I tried this with many boards, and it seems to work just fine. So this is supposed to work. And then A9 and B9, they should go together. If I click A9 and start routing, then B9 gets highlighted, and this is the USB voltage. So I just connect them roughly, and later on I will fix the traces. Then we have ground here, and we can see that actually we have a bunch of ground pins. So R1 has a ground here, the USB connector has a ground here, and we have this 5.1K resistor. So we could in fact create an island or a very thick trace to connect everything together. So I just bring a trace down here, here and here, and also go up here. So I know that they are connected, but again, this is a preliminary layout, so it doesn't matter. And then R1 has to go to the shield. And you can see that the auto routing still wants me to connect all these shields together. But physically they are already connected because the connector itself is a single piece of metal. So physically it's connected together, but still for some reason the editor wants us to connect it. It will throw an error or a warning when we do the electrical rules checking, but we can neglect those violations or alerts because it's not a real error. So we can put them on an exception list. But you can see that, yeah, this wants to be routed together, but you don't need to route it because it's already routed due to the nature of the part. Then we have the CC2 route, and we also have the CC1 route, like here. And I might want to go a little bit here to the right, because I can grab this by pressing letter G and bring this up here. So I get a bit more routing for the USB data lines here. Then we can see what we have here. First, let me do the 5 volt routing. So that comes here. Again, preliminary route. And then I can also do the same with a 5 volt that should go up here. So this is done. And then we can see that we have a bunch of ground here. So maybe instead of connecting these two like this, I can route under the chip, because this is nothing that the load goes through it or anything, it's just the enable signal. And then all these 3 grounds can be connected together here. So maybe I can even make an island. And since we have this, I can come much closer here. And by pressing D at this corner, I can route a bit probably nicer. So they can go a bit higher up here, something like this. And then I just remove the excess trace. And this can also follow it, something like this. So now we have a corridor here for traces if we need it. Then here we can see a funny thing is that the D- and the D+ are twisted. So I have a very dirty trick for this. I delete this trace here. I double click this specific pad. And then I remove the net name so it doesn't want to route to anything. And now you can see that now everything is routed correctly. So D- wants to go to A7, which is one of the D- pins, and D+ wants to go to A6, which is another D+ pin. And why I wanted to do this, because I want to route them with a differential pair. So then in that case, I might move this a bit more up here just to decrease the distance and tame the angles a bit. And then here we can grab a route differential pair option and start from here, and you can see that we can nicely go down, yeah, roughly until here. And now you see that the routing fails, but I can finish this because in this situation it should not matter too much if we differ to some extent. It's a very simple circuit and not a high-speed USB, so this is fine. And then before we forget, we double click B6, and that belongs to D+. So I just select it again, press OK, and then I bring this back like this. So this is now complete. Then we have ground here and here. So what we can do is we just bring it down here. And in the same fashion, we have 3.3 volt. So I just connect everything together. So this was fairly simple. And then these guys can go much, much closer to the chip. something like this, and I just connect them. So this is again just a simple exercise of connecting everything together. This goes down straight, and then here we can be a bit more nice. So this is so far so good. We can see that there is a 3.3 volt trying to go here, but that routing will be solved a bit later. What we can solve right now is that 3.3 volt can go here, and this 3.3 volt can go here. Plus, I can bring this out sideways and go all the way up to our 3.3 volt pin. The ground doesn't need any attention because that is on the ground plane. You can see the 4 spokes here, so that's part of the ground plane, so that's nice. But here I forgot the 5 volt from the fuse. So it's very important that all the parts of the board gets the 5 volt after the fuse. So you cannot even overload your USB in that matter through this pin, because this pin is also limited by the fuse's rating. So this is good. Then we finish this, and I can also finish this by routing a trace here and pressing V to generate a via which goes to the ground plane. Again, I'm still routing in an ugly way. I will clean this up and explain you what is happening. So here we have the capacitor for our microcontroller. I bring it a bit closer, and then I come out from this pin sideways and then just go to the cap, and then I connect this capacitor with this 3.3 rail. And at the same time I can do this with the chip, which is the USB to USART converter. Then this can go to ground very simply, just in place. And then we have the TX and RX pins. So I route them in a bit funny way, and later on I will explain you why I do this loop. But you can see that we have 2 more pins here and a few more at this corner, and they have to be routed towards the top of the board. So I have to be able to come out to put some vias here, so I can route these pins underneath on the bottom layer and bring them all the way up to this position. And the only way to do that is to run the traces at the bottom of the board. And RX also in a similar way, it will be routed tightly around the already existing trace. Then we have our crystal. So the XI can go out straight and then route it here. The 2 ground pins can be connected together like this. And then we have the XO, which can come like this. And then this goes here, this goes here. And as I promised, there will be a ground plane here. So how to do that is that we are still on the front layer, and here we have the field zone, similarly as we did the bottom copper pore. But when I click here, I select the ground layer and I make sure that it is on the front side. So I press OK, and then I just simply draw a rectangle bordering all the ground pins. So we can see that this looks almost okay, but what we could do is that I can make a trace here just to make it a bit better, and probably increase this to 0.4. Then we have a more reasonable connection between basically everything here, so it's a better ground. And then I can place a few ground via here. So if you look at the board, then we have the ground here, so this should be fine. And then we have the button here, which is the reset button. So that is connected to PA7. So I just bring it out and connect it. And this goes to ground. So I just place a ground as close as possible to this component. And that is correct there. And we have the capacitor. So that I just bring it here. And then this should be the ground. So what I could do here is that we can see that this connector has the ground on this side. So I can just rotate this and bring it to the center. Now we have the ground at the other side, so I can just route this ground connection here. And also we have the reset pin here, so I can just route it also to the capacitor. So now the basic things are routed, but we can see that if we start again from the USB connector, we can tidy up things. So for example, here the ground doesn't go anywhere. So what I would do is I would route like an L-shaped trace here, and then click one of the traces, press U to select all, press E to open the properties, and change this to 0.5 millimeter thickness. Because now this is a thick trace, so I could put a few wires here. So I dig through the board, and now we have a direct connection between the top side input here, which is the ground, and then the bottom of the board. So this is now good, and everything is routed with the ground, so that's really nice. And here I could do the same. So I press U a few times, so everything is selected, press 0.5, and again I add a few wires here just to make sure that there is a solid connection between the ground and these traces. This can be also, I press U, press E, 0.5, so it's thick enough. Then this is a bit tricky, but I just selected U, and this should be 0.4, because otherwise I cannot route it out here between the hole and the pad. The software will complain. So I put a break here, right click and break track, and then I can pull this aside, and you can see that I got some errors here. So I just tried to kind of route this in a correct way, something like this. It still violates the DRC, but it won't matter when it comes to manufacturing. And I try to replicate the same. So right click, break the track, and then I bring this a bit inwards, and I press the letter D and try to route it like this, something like this. I can also tidy up this just to make it better. I mean, better looking at least. So this is fine. This is 0.2, but it could be 0.3 if we are really picky about this. The USB can stay 0.2, and then here we have the 5 watt. Since we can have 500 milliamps, this should be also 0.5. And then the routing goes fine here, so nothing to complain about except this corner here. So I fix it, press U, so we have the wall route here, and this can be also 0.5. And then we can clear up this trace so it's routed a bit nicer. Again, 5 watt, U, E, 0.5. This is done. So these are done. We have the forgotten ground here, so this could be also 0.5, let's say. We have 3.3 watt here. We can select the wall routing here, which will cause some trouble here, but that we fix it later on. But something like this. And then the trouble here will be this, but you can move it by pressing M and just bring it back here. And instead we fix this side, so I click somewhere at the edge here, press D, and just route it like this. So this is now fine. And one can argue that one can create an island here again with the field zone, but I think it's good enough this way. It won't do any harm. But this trace here could be thicker, and this trace could be thicker. Then we have this 5 volt, but this is not carrying any current. But to be sure, let's make it at least 0.3. But this is just to have the enable pin under the same voltage as the input pin. And you can see that we missed a 5 volt trace here. So I'm just going to route it. So that's done. And then the ground also 0.5, 0.5. Again, could make an island or a field zone, but it should be fine. So now this is routed together, but there is no ground. So eventually we can put, for example, a few wires here, and perhaps somewhere in between here. This should be all right. Then this lonely pad has a missing wire, which I will put here. And then I just recover this a bit. So this should be fine. And then this pad also misses a ground connection. So I can just go straight here. And then this is done. So these are signal traces, so I don't touch them. They are good at this thickness. But this I can change to 0.5. This is fine. Here again, we already fixed it, and these are signal traces, so we don't need to pay too much attention to these. Here also. And this is also a kind of just a signal pin in some sense, but we can make it thicker if we like so. And now comes the fun part, because we have to route all the left GPIO pins to the corresponding pins on the side. So let me do that. So how we do that is we start with the simplest one, and that is, for example, PD0, because PD0 comes out from here. Then I just route it down here. Then I just go with the flow there. And then PA3 is similar there. And now we are in trouble because this one wants to go up. So press V, and then we go under. And we have the same with the PC5. So we go back. We have PC5. I go up here, press via here, and try to follow this trace closely enough. There. And then luckily we just have one more left, which is PC6. So I place that here, and then I just follow everything here, and we have arrived. So obviously this is ugly, but the worst thing is here that if I press now B to regenerate the zone, then we separated this part of the board from this part of the board. So I will need to pay attention to that and fix it, because now if we just imagine it in a very schematic way, the ground comes here and it cannot go here directly, so the ground goes around this pin and then it finds its way here, and the same here. So that might not be so good, but just now let's not worry about this. However, I want to clean up the traces here. So PD0 is almost fine. Let's route it here, and let's route it like this. So this looks acceptable. PA3 can come a bit closer. PB0 looks horrible, but I fix it. And this is also fine. This we can leave. This can go a bit here. Then PC1 can be this. You can see that it goes a bit haywire, but I fix this, something like this. And there is a purpose why I do this 2 or 3 kinks in it. You will see it later on, why I want to do this. But something like this. And here also I can kind of route a bit nicer. Perhaps I do it like this instead of the initial thoughts. So something like this. This looks acceptable and it doesn't really interfere with anything. And then we have to take care of the bottom layer. So I go to the bottom copper, I change this setting, and actually I can pull this on the other side if it lets me. So I cut the ground layer somewhere else. And now this looks a bit more reasonable in my opinion. Something like this. And I can still see that, yeah, of course there is an island forming here on the ground plane, but I will fix that soon. So we see this. So what I could do actually, and that could be even a bit more fun, that I route one more trace here and I dig down. So actually now through this capacitor I also connect the rest of the ground plane. I don't know how good practice that is, but at least I created a bridge over these traces which run on the bottom side of the plane. So then the ground can still continue on, let's say, this side of the board, which might be beneficial for the crystal. Then we have the SWIO pin, which actually wants to come all the way from here. So that's a bit challenging, so I will route it later. However, we can continue with the easy pins, and that is, for example, PA6. So I just come out with that and just route it like this. And PB3, that can come out straight. And then we just continue with the easily routable traces. And then now we start to see the issue. So we have PD4 that has to go in a via. And then we again chopping up the bottom copper layer, but don't worry about that just yet. So this is how it looks like now, and just a few pins are missing. How I can mitigate that is that I can do a funny stuff here. I actually just remove this trace. I move this in between the pins here, and then now it's easier to route this one in a bit funny way, and then this has to go underneath. And then the SWIO has to be solved as well. So I just bring this here because I don't want to chop up the ground layer under the board. And this is now getting dangerously close to the crystal, so I can again do some adjustments. So now the big challenge is here that I caused by this SWIO pin is that I essentially separated this island from the rest of the circuit, which is kind of a problem because now this place is not grounded, and we need ground connections here because the switch needs a ground. So I have to figure out a way. So the easiest way, in my opinion, is to break up these traces here. And then I bring this way. And then I bring the capacitor to the pin here. So now we have a bit more space. I could actually route it this way, if I could be a bit more aesthetic here. And now what I could do is I bring a big trace here and dig down. And now this is connected, but I want to ensure a good connection. So this goes 0.5. This is a bit higher up, so I can place, let's say, one more wire here. So if I look at the board, now we can see that we have a connection between the ground, at least this ground pin here and this island here. But you can see that these two grounds still want to meet each other. So yet another trace, like here, make it thicker, 0.5. Probably I drag this a bit higher, like this, so this can go a bit higher. And then I add a few wires here, here, and maybe here. So now they don't want to connect anymore because they are connected. So if you look at the bottom plane, so then they are connected together in this sense. So it should be fine, hopefully. And then we can see that the 3.3 volt connection is missing. I come from here and put a wire here, and then I just try to cut this the least, let's say, destructive way as possible. But of course that won't work so nicely, but it works. So you can see that still we have a little gap here which brings down the ground to this plane. I can clean up a bit here to make this gap wider so we can have a better, let's say, flow here. So now it's a bit more wider, so that should be fine. However, we still have an island here, which I don't really like. So we have to mitigate this. And how we can solve it is we grab this. Now we have the ground on the correct place, so we just clean up the traces. So now this is traced more or less properly. So we can see that this part is fine. And there are no islands in that sense that here there are no parts that we can kind of block out from the ground plane. So that's good. And then here, now finally this capacitor goes to the ground plane, which is then here is an island, but it's connected to this other kind of an island. And then that is solved. So everything gets enough, let's say, ground, hopefully. But then, since I separated the ground with this 3.3 volt trace, this is not really needed. So I can get rid of this because the capacitor is connected here. So now this is good. And then we can look through the traces one more time. So front, and we can see if the auto routing wants to route anything. But here at the bottom we can see that we have all the connections for the programmer. So SWIO, 3.3 volt and ground. Then we have the switch. It is connected to the microcontroller, and also the reset goes to the reset connection here on the pin terminal. The capacitor for filtering is connected, so that's fine. PA0 is routed correctly. Then we have these traces going to the pin connections correctly. We have the crystal hopefully correctly connected. GPIOs look fine. This is a bit crowded, but everything seems to be fine. Bypass capacitor for the microcontroller is fine. And then here I want to discuss something. You can see that this pad for the microcontroller right now is numbered as 33, but this should be 0 because the 0 pin is the ground pin of the microcontroller. If you don't remember, then that is pin number 0, VSS, and then this has to be also the VSS. So I open the properties, and this has to belong to the ground plane, and the pad number is in fact 0. So then we can see that the pad wants to go to ground. So what I do is that I create a wire, and now you can see that this wire tries to snap to the graphical element, but I don't want to route it there. So what I can do to prevent this is preferences, and in the PCB editor we have to find the editing options, and these magnetic points have to be like disabled temporarily, and now my wire can go anywhere. So how I would do this is user drawings, and I draw some rectangle, let's say from here to here, just as a guideline. And then I can put one wire here, something like this. This is almost like a thermal wire. So this is now nicely routed here. So continuing the way up, we have TX, RX, they are correctly connected. Bypass for the chip for the USB to USART is connected. Everything is nice here. We have the correct capacitors around the chip. We have the diode, which is the LED. Here what we can do is that we take the front silk screen layer and we draw a small triangle here, something like this. So this will show the polarity of the diode. So that's good, because then we see how to place it. Then fuse is fine, although I might change this to 0.5 and this one as well. And then the rest of the connections look fine. So what we can do now is the next, let's say, appearance related stuff is that if I open the 3D editor, we can see that, alright, the traces look how they look. It now cannot be improved too much, but I will do it. But you can see that there's a huge mess with the silk screen. And eventually you don't need the name of the components here if you first of all know where to put them, or if you want to have them assembled by PCBWay, because in the production files that we will generate very soon, actually all the positions are noted, so the machine will know it without seeing where to put F1 or C7 or U1 and so on. But if you put it together at home and assemble everything by yourself, you might want to rely on these letters anyway. So I will just change their size and orientation and lay them out more or less nicely on the board, so we can then assemble the board ourselves. So now it looks a bit more acceptable. Of course, some of the text is cut by the vias, as you can see, but still it's recognizable. Or if you really want, you can move C7 here, R6 here, and you can do further adjustments, but we have to keep in mind that we have to name the pins here so we know, yeah, which pin is which. So therefore I kind of try to keep this line here and here empty. However, we see that the diode symbol here is a bit obstructing the place here, so I will move it here on the left side, but otherwise this seems to look a bit better than previously. So I put the diode symbol here, and I also rotated R1, so everything is now in the correct orientation. So this seems to be fine. So now, again, another kind of boring job is to mark all the pin names here and here. So it will be a similar text saying that A1, A2, A3, and so on and so on. So we will be able to identify the pins. So I named all the pins, and you can see that they are laid out and not really overlapping with anything, so they should be fine. And I also named the programming pins here, so GND, SWIO, and 3.3 volt. So we can identify everything. So now comes the fun part, which is the following. So we can also put our signature on the board because there is some free space here and there. But I want to make it in a bit more fun way. So we select the front copper layer and we put a text somewhere. And I typically write the initials and the year when I design the board. And let's say I just use a small font size, so 0808 and 02 thickness. So that actually fits here nicely. So I place it like this. And if you look at it, this will be just a boring front copper with the cover on it, like the same as a trace. But if I duplicate this, Ctrl D, place it exactly over the original text, release it, press E, then I can select front mask here, press OK, and what this does is that it reveals the copper layer. So Alt 3, and now you can see that they are exactly the same color as these rings around the pins. And this is actually now an exposed copper layer, which can look very nice, especially if you use, for example, any coating or surface finish. So I leave it like this, and of course you can use your own text, obviously, if you want to design your own board. And we can go on the bottom silk screen. We have a lot of text here, and what I usually do is that I put my website address on it, something like this. And this can be a bit larger, so 1.5, 1.5, and let's say 0.25. And just place it on the center. So Alt 3. And there we go. And if you haven't visited this website yet, please go there and check it, especially related to this demonstration, because I wrote an article about this process. So if you don't want to follow the video, or you feel like you missed some things, you can check the website and probably you will see some resources there as well. So now coming back to the board, this is almost perfect, but I want to show you something because a lot of people are asking this, how I make curved traces. So there is a plugin. So under the tools, there is this external plugins, and you can just search for this round tracks plugin, and then it's literally just, you have to press run. So then it will generate the nice rounded traces. I usually regenerate the ground plane after this, and then I have to look around if there is any short circuit, but typically it does the job perfectly. But now we have very nice curved traces all over the place. And what we can do now, since now the traces are more or less permanent, of course we can always go back, but we can do design rules checker. And as I said, probably the missing shield connections, according to Kicad, will throw an error, but otherwise there should not be too many errors. So we run it, and we have 3 errors. So this footprint error is not really an error, but it's a warning, so the footprint doesn't match this, but I always get this and never causes a problem, so this is fine. But we have 3 unconnected items, and guess what? It's the shield. It's always the shield. So as I said, we can just neglect this, so we just ignore it, exclude this violation, exclude this violation, and exclude this violation. So if we look at this window now, we have 0 errors, nothing went wrong. So we can see that if I haven't done any mistakes, and hopefully I haven't, because this board has already been produced, or a very similar one that I have shown in the previous video, then this can go into production. And how it goes to production is the following. So we have to first place an origin for the grid. So I just place it here where the corner of the board can be found. So I just place it there. Plus we can place the pick and place. So I just long press on this and then I release the mouse over this icon. And then I place it also here. And this is useful if you want to get the board assembled by PCBWay, because they need this information for the pick and place machine. So when the machine assembles your board, then it will know where to put each components based on the coordinate system that we just defined right here. So we can immediately export this file. So we go to File, Fabrication Outputs, and Component Placement. So I already created a folder for the Gerber files, so I just place it there, and then I just generate this file. And then we go to Plot, and then we start with the drill files. So again, this goes under the Gerber folder, Generate, and then I just simply press Plot. This is also done. I close this. Then I open that folder. Then I take all these files, right-click, and compress as a zip file. And now we go to PCBWay.com and place an order. So we go to PCB Instant Quote, and then we select the Upload Gerber Files option, and then we add the Gerber files. So I have already prepared it. This is the Gerber file that I just created, so I open it. And now we can see the board, very nice. If I zoom in, maybe a bit more is visible. So here is the front side of the board, and here is the back side of the board. And then if we go through the options, we can see that we should select the quantity. So I usually order 5 or 10 pieces. It doesn't really matter in these small quantities because it will be still a very cheap price. It's a 2-layer board, so we don't need to change this. The material is also FR4. This material, the base material, is also the same. So we use the 150 to 160 glass transition temperature board. The thickness of the board is regular 1.6 millimeters. Track spacing is also the same. Hole size is also the same. We did not choose any fancy vias here. And the solder mask is up to your requirements. As you can see, the green color results in a very cheap price, but also the red will be the same. The only exception is that it will take a bit longer time to produce, but 3 to 4 days is still good, and PCBWay is usually faster than that. And then silk screen can be also changed, but keep in mind that different colors might end up costing a higher price. Then we don't want any color printing because we don't have any graphics. We don't need any edge connectors, and the surface finish can be kept as a default. Or if you have more money, then you can use the immersion gold, because then the exposed parts will be coated with gold and it will look very nice. And then wire process can be left as is, so tenting wires. Copper thickness can be left as the default, and I usually remove the product number because I just don't want it to be on the board. So it costs a little extra, but I think it's worth the price. And then if you make the board yourself, you have to select the stencil because it makes your life easier. And then you have to select the non-framework stencil because that will just result in a simple steel sheet. And that's what you need because it's much easier to handle, and also it decreases the shipping costs because it's a smaller piece of material. And here I usually don't change anything else except the thickness, because I learned by the time that 0.5 millimeter might end up spreading too much solder over the pads, and that is not always good because then it's much easier to get solder bridges. So I go for the 0.1 millimeter thickness, and this is particularly important for this board because the microcontroller has very densely packed pins, so it's better to use the 0.1 millimeter. And then I don't change anything here. On the other hand, if you don't want to make the PCBs yourself, then you don't need a stencil, but you have to select the assembly service option. And then here you have to go for the turnkey, so everything is supplied and assembled by PCBWay. And then you have to fill in the quantity, and then you get the other parameters filled in. This can be filled up, so then it makes PCBWay's work easier. And then if you have any other fancy options here, then you can also select them. And when you place the order, you can finally upload the files, which I provided on my website and also on my PCBWay project page. So you will have the bill of materials that PCBWay needs. And then you can finish your order once PCBWay reviewed it. So now you know how you can create your custom microcontroller PCB. So once again, if you want to have a bit more resources, please don't forget to visit my website. Link is in the description. And also, if you want to order this board without designing it, please visit my PCBWay project page, because I shared this board design on my project page, so you can just directly order it from there without the need of designing it. And if you like this kind of content, please consider becoming my supporter on my YouTube channel. So please consider becoming a YouTube channel member. That can help me to buy more gadgets and make these kind of tutorials and spend more time on it. So it's a mutual benefit for us. So I hope you like this video. I hope you learned something, and see you in the next video.